Prism from Critical Blue helps software developers migrate their sequential applications to run effectively on multi-core platforms. Prism runs as a plugin to the Eclipse IDE and is included in Intel's Signal Processing Development Kit along with the Intel C++ Studio XE tools for Linux. We'll be adding parallelism to an open-source JPEG encoder application, and in this case, targeting an Intel Sandy Bridge IA platform. The JPEG encoder works by breaking an image into rows and columns of macro blocks. In the original sequential implementation, JPEG 00, one macro block data structure is created and shared by all encoded iterations within the row-column loop nest. For each macro block, the pixels are color converted, DCT transformed, then quantized, and finally Huffman and run length encoded. We use Prism to collect a detailed trace of the encoder's activity, and we switch to the Prism perspective to load in the trace and focus on the area where the JPEG encode function is active. We are interested in how the software will run on a Sandy Bridge platform, so we select an i3 part, a dual-core device with hyper-threading, so we will have 4 virtual cores. Switching to the function profile view in Prism, we see that the macro block encode function is doing all the work and is called multiple times. The DCT is the most expensive function in the encoder. Without making any changes in the original source code, we can ask, what if the macro block encode functions were run in parallel on the i3? Could it be that easy? And we hit the apply button to see what benefits we would get if we had actually coded it up. Good thing we didn't code it up, because the encode functions don't appear to run in parallel. If we switch from a by-core schedule to a by-task schedule, we see the encodes are running one after the other. Zooming in on a pair, we see a dependency arrow between them. Right-clicking on the arrow brings up a long list of dependencies. Many of these are write after write and write after read dependencies, which are often the result of shared data structures. Looking at one of the color conversion to color conversion dependencies, we see that source and destination are on the same line, which normally indicates that the dependency is carried between loop iterations. The macro block pointer is the issue in this case. Remember that we shared one macro block amongst all iterations. The scheduler can't run the encodes in parallel without clobbering that single macro block data structure. In the dependency view, the other write after write and write after read dependencies are all related to this shared macro block. A simple solution here would be to create an unshared local macro block for each separate iteration. The read read after write dependencies, which are in Huffman subfunctions, should also be considered, but let's go ahead instead and code up the local macro block solution, thread the loops, and see what happens. We've done that in Design JPEG 1 and loaded in the resulting trace. We see great utilization of the cores, but unfortunately we have race conditions detected, which indicates that we failed to properly synchronize some dependencies. When we zoom in, we see red data race arrows. Some arrows going backwards in time suggest that we tried to read a value before it was written. Right-clicking takes us to the read after write dependencies we ignored earlier. Picking the first one shows that the encode data unit function for a new macro block starts by reading the previous macro block's DC value to compute a DC difference, and later on, the new macro block's value becomes the DC value saved for the next new macro block. Honoring this dependency requires that the macro block's Huffmans be encoded in order from first to last. At this point, we can ask, what if we fix these races? What then would the schedule be? Hitting the apply button computes the new schedule, and we switch to the by task view to see the result more easily. Each macro block's Huffman encode is delayed long enough that all the Huffmans process in order. Zooming in, we see the data race dependencies are now all going forward in time in this schedule. This is close to an ideal result, but will require some extra work to properly synchronize. Is there a simple fix that's good enough for our needs? In Design JPEG 2, we decided to simply pull all the Huffmans out of the loop. We'll do everything else in parallel, and then run the Huffmans sequentially at the end. In the loaded trace schedule, we see no data races now, and the short tail of the Huffman in green at the end, just as we expect. Running on an i3 with 2 hyper-threaded cores, this may well be good enough. Remember the discrete cosine transform? The DCT was quite expensive. What would happen if we rewrote it using Intel SSE or AVX instructions? The answer is in Design JPEG 3. The new DCT is 3 times faster. The Huffmans take the same number of cycles as before, but now they look like a significant sequential bottleneck, a good demonstration of Amdahl's law. Design JPEG 4 tries to hide the sequential Huffman latency by adding a priority queue, trying to greedily run the Huffmans in order as early as possible. The resulting implementation trace schedule shows no races and looks similar to the nearly optimal what-if schedule from Design JPEG 1. For this demonstration, we haven't touched on the tuning capabilities within Prism. Insight into issues such as cache misses and invalidation, branch mispredicts, synchronization bottlenecks, and hyperthreading effectiveness are analyzed to further optimize application performance. In particular on multi-core architectures, memory subsystems are much more performance sensitive than on single-core platforms, and this is an area of rapid feature innovation driven by our customers. In summary, we started with a sequential JPEG encoder and iteratively refined it to a nearly optimal parallel solution. Along the way, we used Prism's exploration capabilities to understand what benefits we can expect before we made any code changes, and we made some mistakes which Prism caught and helped correct. If you'd like to try this example yourself, or try it on your own application, a full-featured 30-day Prism evaluation license is freely available at www.criticalblue.com/prism/intel. Give it a try!